Welcome back. We're going to be figuring out how work and kinetic energy go together and how to actually calculate not only work, but how that affects the total amount of energy, especially the kinetic energy. So let's get into it. The Work-Kinetic Energy Theorem says that, hey, if you add up all of the things that are doing work on your system or are transferring energy to your system, that's going to be equal to the change in kinetic energy for your system. So we'll get into the specifics here of how that actually works. On the left side, this sum of all the works, you're going to have a work term for each and every force that you have on your system. And then we'll calculate the amount of work done on work for each of those forces based on what we found out before work is. Work is the change in energy, and how do you actually calculate that? Well, it is a force dotted with a displacement vector. That's a dot product there, remember? What does the dot product mean? The dot product is that force times the cosine of the angle between that force and the displacement vector. What does that mean? That means it's just the force that is parallel to that displacement vector that you're multiplying against each other. Okay, so that's how we calculate any force and how much work it's actually doing to change the system's kinetic energy. Now notice that we're not using any potential energies. We've talked about potential energy so far in general terms, but we haven't been able to calculate yet what potential energy is. That's going to be the next step. So here we're just doing the forces that are acting on the system doing work on the system, and therefore are they changing the kinetic energy of the system there, and we'll get to potential energy next. Okay, so on the right side, we can change the kinetic energy. We're referring back to the Work-Kinetic Energy Theorem, but we don't have any formula for kinetic energy yet, so let's see if we can figure that one out here. So we know that work is equal to the change in kinetic energy, and that's just the force dotted with the displacement vector. Remember, that's a dot product, it's not just multiplication there. And so we'll go and we'll say, hey, not just force is equal to ma, but the sum of the forces is equal to ma. And if I go and I put that in, because this is actually the sum of all the works, and so I could think about this as the sum of all the forces there. So we're looking at the total amount of energy transferred, so we're looking at the total amount of force as it relates to the displacement vector. So if I take this and I put that in for force, I'm going to take ma, and I'm going to replace that force with ma there, and I'll get this thing right here. So now my force is now just m times a, and then dotted with my displacement vector there. So going back to kinematics, if you remember this equation from back in the day, depending on how much you use this, you could have not used this at all, or maybe you used it a bunch. Where did that come from? Well, we really only have two equations from our kinematics unit, from motion and how how acceleration affects motion over time, and how velocity changes with that as well. That was looking at the position time, velocity time, and acceleration time graphs, and we got these two equations from that. If you take these two equations and you combine these two equations and you eliminate time, and then you solve for v squared. If you've never done that, go try that. It's just basic algebra that you're doing, but you have to do a fair amount of steps to be able to get there. When you go and do that, you get this guy. So that's just the algebraic combination of these two things. It's not actually a new formula, but it's useful, especially when we get to more complex stuff, as we're kind of getting to. We won't use it too much this year, but if you go and take AP Physics C next year, you'll be using that a lot more. So anyways, this is true, and it's true because it's just the algebraic rearranging of these two formulas there. So now if I take this thing and I rearrange it, so I solve for acceleration. So how could I do that? Well, I could move the v naught squared over to the other side, so that's v squared then minus v naught squared is equal to 2a delta x. And now I need to move the 2 and the delta x over to the other side, so I can do that by simply dividing both sides by them. So I get now, I'll just do that in one step here. So now I'm going to divide by 2 delta x on both sides, and that's going to cancel out the 2 and the delta x there, and we'll be left with acceleration on this right side there. And so we get exactly what's written over here, so that's how we kind of go from there. And so then, excuse me, we'll go and we'll take this and we'll plug it in for where we see acceleration there, since it's equal to acceleration. So now I have just that original m, but now multiplied by not acceleration, but this whole thing that is equal to acceleration, and then still multiplied by delta x. So currently we're kind of assuming that this force that we're talking about here is going in the same direction as parallel to delta x. And we know that that's how you actually resolve this dot product here. And so assuming that we're resolving the dot product correctly, that's a reasonable assumption to be able to do this algebra. Okay, so moving on. We're down the list, this line, we know that it's equal to delta x. And the delta x's cancel out. Check that out. We have a numerator here and denominator over there. So I can see that things on the top will cancel out with things on the bottom there. That's kind of nice. If I take this 2 that's in the denominator, I'm just going to move that out to the front because why not? Kind of cleans it up a little bit. So now I have that 2 that's over here, so there's the 1/2, and then multiplied by m, and then whatever's left in the numerator there, which is v squared minus v naught squared. Remember, that's just the some ending velocity minus some beginning velocity. So now let's go ahead and let's distribute this 1/2 m to both of these things here, and it'll help us see what the kinetic energy actually is. Okay, so look at just the left side here. So I just multiplied the 1/2 m by each of these v's here, and so I get these two guys. But then I'm going to go and expand the delta x, and I know that the change in anything, just like in math class here, we had the slope was always the change in y over the change in x. And when you went and did that math class, you said it was like y2 minus y1 over x2 minus x1. That's how most people have written it in math. What are you doing? You're just taking the ending bit, the second thing, subtracting it from the first thing, the beginning bit, you might say. So usually in higher level maths, as well as science, instead of writing y2 and y1, oftentimes we'll write it as some ending y minus some beginning y, and some ending x minus some beginning x. So we go and do that because it's just as hard as the y2 minus y1, but it's a little bit more accurate in some ways. So then we go and do that over here, and we go, oh, it's just some ending kinetic energy minus some beginning kinetic energy. Now notice, this was a little math trick that we did here. If I distributed this 1/2 m, which is kind of counterintuitive from what you've done in math thus far, but if I did that and then expanded this delta x, I can see something really interesting here. Check this out. This v is the ending v. And so then this whole term right here, it relates to the mass and the velocity at the end. Well, look at the right-hand side. This kinetic energy is the kinetic energy when? Well, that's right, at the end. At the same time that this v is whatever that is, it's going to be equal to that kinetic energy right there. Huh, interesting. And notice what else also happens. This is the velocity at the beginning, and the mass of that thing at the beginning, we're assuming the mass isn't changing here. And so then this term represents all of the bits of the thing at the beginning that are moving and have some mass. And this represents the kinetic energy that's at the beginning there of when you have that velocity is actually 0. Oh, so notice when I write it like that, I can actually see that the ending kinetic energy is just equal to that, and the beginning kinetic energy is just equal to that. So then in general, I can say that, hey, my kinetic energy is 1/2 mv squared, where some whatever v at any different point is the kinetic energy at that point there. Neat, neat. Okay, so that wasn't too bad. All right, let's move on and let's put this into practice. So this is kinetic energy, and we did all that so that we can actually make sense out of this Work-Kinetic Energy Theorem, that every time that I have a force, I know that that force may change the amount of energy of that system, and therefore may change how fast that thing's going, aka it may change the kinetic energy. So let's go see how the sum of the work actually works out, you might say. Going on to the second page here. From conservation of energy, we know that we can't create or destroy energy. And we also know that if we have an object, or two different objects, A and B, if object A exerts a force on B, so let's take the classic example that you did a lab for, where I had a box. You actually had two boxes here, but I'm going to use a person pushing on that box. So I'm going to take a person, and they're going to push on that box. They're going to push parallel to the floor there, and we'll give them some hair here and put a big smile on their face because they're doing physics. If they're putting a huge force going this way, and that would be some sort of normal force. So person, this is the normal force that's on the box by the person. Well, if I go, well, is that the end of the story? Oh, no, that's not the end of the story. They put a force on that box, but then, well, they get a force on them, right? On their hands right here. This is the force starting on their hands. On their hands, they push on the box. True, there's that force right there. But then don't they feel the box pressing against their hands? Yeah. And so they would feel that resistance, you might say, on their hands there. And so they would feel a force that's going this way. And this is the normal force that's on the person by the box. And if I compare these two, and I drew them a little bit wrong here, I had to draw this about the same size. If I compare these two forces, I can see that these forces must be the exact same. We measured that in the lab with those two boxes as we moved them along at constant velocity or accelerated them. Okay, so then if object A, person, puts a force on object B, we know that object B is going to put a force on object A. So according to Newton's third law, object B, I'll just say pushes A, right? It exerts the same amount of force on the other object there. All right, so then both of these forces have to be exerted through the same distance as well, right? Let's make sure that makes sense. We go back up here and you go, hey, if I started here and I ended pushing that box there, I'd be pushing that box through some displacement like that. Well, the whole time that I'm pushing it, is the box pushing me? Well, I mean, can you feel that the box would be pushing you the entire time you'd be pushing that? Well, sure, I'd have to be pressing against that box to make this blue normal force that's on the box there. And if I'm pressing on the box, I'd feel that resistance in my hands and my arms and the rest of my body. And so then, yeah, I could feel that I'd have this normal force that the box is exerting on me, this red one here. So no matter how long I'm pushing that for, whatever distance I'd be pushing that through, then it must be pushing on me through that same distance as well. Okay, cool. So the force is the same, but also the distance that it's through is the same. And notice we're not measuring time here. We could measure time, but that doesn't equate to energy as we saw in the last one. Therefore, if one of the forces is in the direction of motion, it will do, well, which force here is in the direction of motion? Well, the normal force on the box here is going with that displacement vector. It's parallel to it and pushing in the exact same direction. Notice that they're both actually parallel. Both forces there are parallel to that delta x, just one is going the opposite direction. So now, therefore, if one of the forces, this blue one here, is in the direction of motion, it's going to do positive work. And we're talking specifically our system right now. All right, well, let's draw it like this. Our system right now is this box right there. The other force must be against the motion, so it will do equal amounts of negative work, and now that's negative work, but notice that force isn't on the box, so it's not negative work on the box there, that's negative work on the person. Okay, so what does that mean? Well, as I push this here, might I be speeding that box up? Right? If it was frictionless down here, if I'm constantly applying a force, I would be causing that box to go faster and faster and faster. Well, the box is pushing against me, and so I'm making the box go faster. Is the box making me go slower? It's kind of a hard question there. If the box wasn't there and I was trying to move, might I be able to move faster because I'm not pushing on this box? You can imagine like a big heavy box, like you're trying to push a refrigerator across the floor. You go, yeah, if I wasn't pushing on that thing, I'd be able to move myself faster. with the same amount of exertion, with the same amount of energy? Oh, yeah, I probably could, right? I could probably use the same amount of energy and that I would pushing a big, heavy refrigerator across the floor. And I could take that same amount of energy and run across the floor, and I would be moving way faster when I'm not pushing on this big refrigerator there. Okay, so then is the box, or the big heavy refrigerator in this case, is that doing negative work on me? Well, it sure is slowing me down using the same amount of energy in those cases there. So then it sounds like that is doing a negative amount of work there, where it's changing my energy, but in a negative fashion. I'm not able to move as fast. Okay, therefore the energy that one object gains, the other object loses. Okay, so I am pushing this box, making it go faster, and the box is pushing me, inhibiting my ability to go faster, you might say. Okay, so then therefore we see that the total amount of work done on the systems must be, what do you think, when you add these two together, what do you think you're going to get? Well, if you're not sure, think about what work is. Let me do that in a different color. What is work? Work is the force dotted through, remember that's a dot product, dotted through that. What does the dot product mean? It's just the force times the cosine of that angle, or an even simpler way to say that is the force that is parallel to that displacement vector. And so you go, okay, great. Well, let's compare them. Would it add up to be positive, negative, 0? I don't know. Let's compare them. Well, let's compare the forces. Tell me something about the forces. Same force, same amount, different directions. Okay, great. Tell me about the displacement vectors of the box versus the displacement vector of the person. Same as what we described before. Okay, great. So then these numbers here that I'm going to put in are exactly the same. They might have different directions, and what does the direction tell you? Well, if they have different directions, right, this angle is going to give you either a positive sign going with it when the cosine of the angle, theta, is 0. But when it's going opposite of it, well, if I measured from, let's get a nice purple color. If I measured from here to, it looks a little bit weird, over to here, look at just the angle, how many degrees did it go through? You go, oh, well, you just did 180, you're going the opposite direction. Well, the cosine of 180, quick quiz, cosine of 180 degrees is, you guessed it, -1. So then when I go and put that in, I get a negative sign there. So then I have force, delta x, and a negative sign. And so I get negative work when I'm doing this red force that's on my person with the delta x there. So then they must add up to be exactly 0. Okay, cool. Then the change in kinetic energy of the universe. So if I made my system not the box, but I made it the whole universe. So I'm including absolutely everything there. Then the change in kinetic energy of the whole universe is, well, it's got to be 0 then. Oh, that's why we labeled it as the conservation of energy here. We started with Newton's laws here, and we can deduce that energy cannot be created or destroyed, and we can kind of prove that too. Okay. Therefore, the total energy of the universe is increasing, decreasing. It must be constant. Okay, you can't create or destroy energy. And this concept is more important, is important enough to have a name. It's the law of the conservation of energy. Energy can neither be created nor destroyed. And I'm sure you've heard that before. Now, quick note, have you ever heard of the law of conservation of mass? Maybe you did in chemistry there, and you go, well, those sound really similar. And there's a famous equation that you probably have heard of before, and it's this thing. Guess what E stands for? Yep, energy. Guess what M stands for? Easy. Mass. C? That's the speed of light, which is generally a constant. Through a vacuum, it changes with going through, like, whether it's air or water or something, glass or something like that. But it's really, really, really fast. It's like 3 times 10 to the 8th meters per second, which, how fast is meters per second? Well, that's 180,000 miles per second. It might be 186,000 miles per second. Oh gosh, I gotta go look that back up. But it's right around there. So that's really, really, really fast. So now, wait, check this out. What does this equation say real quick? It says that if I take some mass and I multiply it by some really big number, I get energy, which means that if I take mass, I can convert it into energy. And vice versa, if I could take energy, I can convert that into mass. This equation is monumental because it's saying that mass and energy are actually two different forms of the same thing. So now, how does that relate to this? You go, well, hey, if I can't create or destroy E, then, hold on, let's think about it the other way. If I accidentally created mass, I would also be creating then energy. Oh, and so if I can't create or destroy energy, then I must not be able to create or destroy mass as well, and vice versa is also true. I'm pretty sure that this is 186,000 miles per second. I'll go look that up afterwards and put it in the comments. Okay, using the Work-Kinetic Energy Theorem, let's get like an actual example here. We're going to take some steps to go through, and we can see this concrete example of what's going on here. So we have we need to deliver some physics textbooks upstairs there, so we make a nice big ramp on top of the stairs there. These are the stairs going down there, and here's the nice big ramp, and we're going to push that crate of textbooks up there. It's a real ramp and everything, so we actually have friction going on between there, and we can see that it's given an initial velocity of 40 meters per second at the bottom of the ramp, got some coefficient of friction there, specifically kinetic friction since it's sliding along there. How far up the ramp will the crate slide before coming to a rest? Okay, cool. So we're not actually pushing it up the entire time. Notice how I read that. The crate's given an initial velocity of 4 meters per second. All right, so we get like a team of people, and they all shove it, and then we get it going at 4 meters per second. V naught is equal to 4 meters per second. We get it going that fast right at the beginning here, and then just let it go. It'll go, how far is it going to slide up there? Probably not how we would actually do it in reality, but we can make an easy problem out of it anyways. So then we're going to choose our system, and in this case we choose the crate, so I kind of put that in my circle there. Choose the starting and ending position. So where's the problem going to start that I'm doing the calculations, and where's the problem going to end when I'm doing the calculations? So it would make the most sense that we're doing bottom of the ramp for the start, and then where it stops up there, so the ending velocity is 0. That's the stopping. We'll do final because we have stop right there. That's the final position. So initial position I'll put here. Initial, final, start, beginning, start, ending. It's all the same thing. So it's going to be like some space up here. Maybe it'll be right around there where the velocity is 0, and that's my ending bit up there. So draw a free body diagram. Makes sense. So I go over here and we go, hey, the box is pressed into the ramp here, and so that's going to produce a norm force coming out of the bottom of that ramp. Gravity's clearly pulling it down, so from the center of mass of that thing going straight down towards the bottom of the page, towards the center of the earth. And then it's sliding along. There's going to be some friction. It's going to be kinetic friction there, so I'll put a little subscript K there for kinetic friction. Careful, don't get kinetic friction mixed up with kinetic energy. Two different things. And notice there's no push from us pushing it because, well, we're starting the problem after we've already given it that push there. Okay, so it's already moving. We're not pushing it anymore. And so now we use the Work-Kinetic Energy Theorem, and we're going to write a work term for each force, or every force. And notice there's 3 different forces there, and then we're going to expand those kinetic energies. Before we go on, though, I would probably do one more thing, and let's look at this mg. And you go, wait, hold on, I'm on a ramp here, and so I'm going to choose a coordinate plane, whatever I think is appropriate. And I go, hey, my coordinate plane here, I don't want to use the normal x and y. I'm going to use parallel and perpendicular, parallel to the ramp, perpendicular to the ramp. And now when I look and compare these vectors here, normal force is going in the perpendicular direction. Great. Frictional force is going in the parallel direction. Excellent. The mg, the force of gravity, is going in 2 directions. So I need, you guessed it, component vectors. So I do component vectors. That one's supposed to be perpendicular to the ramp there, and that one looks a little bit better. And this one's going to be parallel to the ramp. And so when I do those, I'm always looking at the ramp or this other force that I've also drawn in there to make sure it's parallel and perpendicular to those. Put in my angle, the 20 degrees goes right in here. Yes, it does. You can go prove that many ways. Make sure that you do that. I'll go label these guys. This is mg cosine theta, and then mg sine theta. Which one are we going to use in this problem, I wonder? Let's go find out. Well, on the next page here, we go sum up all of the work, and that's equal to the change in kinetic energy. So, well, what are the work terms there? Well, it's all of our forces, and I'm going to go sketch this free body diagram crudely right here, and I'll do it with a box there. And here's my box, and here is my normal force. We had mg going down, mg. We had frictional force going along the ramp there, and that's kinetic friction. And then in a different color, I got component vectors for mg here, and the 20 degrees in here. Okay, cool. So then I gotta see each one of these forces. Is it producing some sort of work? Is it doing work, I should say, on the box? Is it changing the energy of the box? And so I do work term for gravity, force of gravity, work term for this normal force, and then I say, hey, maybe the frictional force is doing some work. So I just put a W with a subscript of each force there. If I had 7 forces, I'd have 7 different work terms. If I had 1 force, I'd have 1 work term here. And that's equal to the ending kinetic friction, the ending kinetic energy minus the beginning kinetic energy. Notice they put an F there for final kinetic energy. Sometimes you'll see people write it like that. Or if you just wrote it as a K without a subscript there, that is acceptable as well. So now some of these things are going to be 0. They won't do any work. And so if they don't do any work, then it's going to be equal to 0 value, and they'll drop out, you might say. They won't play a role in there anymore. So here it says the normal force is 0. Why does the normal force do 0 work? Well, you go, oh, let's draw the displacement vector. It was going along the ramp there like so. And I go, hey, that's right. Work is equal to the force dotted with the delta x. And how do we deal with the dot product? Well, it's just the force times the cosine of the angle between those two things, force and delta x. Or simply, it is the force that is parallel with delta x. And I go, is the normal force parallel with the delta x? Nope, it's perpendicular to it. So there's no parallel bits there, so I have nothing to multiply, so the work must be 0. A more mathy way to say that is, hey, look at the delta x and that normal force, what angle is between them? 90 degrees. Well, the cosine of 90 degrees is cosine of 90 degrees. If you're not sure, you're doing that on your calculator right now, and that's a big fat 0. It's a bad 0. But it's a big fat 0, and so 0 times anything is just 0. So the normal force comes out to be 0. So one way that we write that in math is something like that, where we're saying this term is going to 0 or is equal to 0. Kind of a simple way to save yourself writing another step there. And so then we also know that the ending kinetic energy is also equal to 0, because we said that the velocity at the end was equal to 0. So now we have this, we can simplify that a little bit and say, hey, maybe gravity does work on it, maybe the frictional force does work on it, and that's equal to the negative, because there's that minus sign, of the kinetic energy at the beginning. Okay, so this line is the work-kinetic energy theorem, but without all of the 0 work terms. So you've already done all of this mental gymnastics here to figure out what is actually going to be doing work on your system and what will not. And remember, work is just the transfer of energy. So what forces are going to be transferring energy over this displacement and which ones will not? Notice that this normal force changes nothing about the energy of this box here. Okay, so then now we plug into the equations for work, as we already wrote up there, that it's equal to F times the cosine of theta times delta x, and that theta is defined between delta x and that force there. And we plug in what kinetic energy is 1/2 mv squared. So we just put all that stuff in. We see, hey, this is the work term for the force of gravity there. This is the work term for that friction there. And remember, this was the negative of kinetic energy, and that's where that minus sign comes from. So it's the friction times this stuff and the force of gravity times that stuff. And we go, wait, what is friction? Well, friction is just equal to that mu, the Greek letter mu, the coefficient of friction, times the normal force there. And then I go, oh, well, hold on. What was the normal force there? Well, we look back up here on our free body diagram, and we'd written on the previous page that mg cosine theta was this guy right here. And we knew from summing up the forces, I'll do that over here in a different color. Oops. We know from up here, if I go and sum up the forces in the perpendicular direction, so in and out of the ramp there, I know that anytime I sum up the forces in one direction, it's equal to m times a. And in this direction, going in and out of the ramp, tell me what acceleration is. It's 0, right? It's not speeding up going off of the ramp, nor is it speeding up going into the ramp. That would be weird. It'd be like springing off the ramp or crashing through the ramp there. And so then we know that the acceleration then must be 0, and 0 times any mass is just equal to 0. So that means that if I go and add these up, I get the normal force there minus mg cosine theta. That's equal to 0, which means that we know what the normal force is. It's equal to mg times the cosine of theta. Well, that's useful because now I can take this guy and I can plug it right in there for that normal force. So let's go do that. So now I have the frictional force is equal to mu times mg cosine theta. Okay, cool. Notice I'm like eliminating a variable there. So now I have more mg's and thetas, but I have less variables to worry about. Now that is also helpful when I realize that the force of gravity, as we've commonly written, is just m times g. Now we can see that there's some similarities here. So if I go and plug all of that stuff in, I get down to this line right here. And let's look at this line here for a second. I look at that and I go, okay, this was just the work term for the force of gravity. This was just the work term for friction. And remember, this was just the negative kinetic energy there. So then, well, I put in the angles between them, 110. Remember, that's going to give me something that's negative there. And this guy is going to be a cosine of 20. Oh, sorry, that's just from mg times the cosine of theta there, and then cosine of 180. Wait, this is going to give me a negative. This is going to give me a positive value. That's the force. No, that's going to be giving me negative. What am I saying? That's negative. And they're both going to be negative because they're both going against its motion there. Hello. Notice as I go along, I always try to double check myself because I want to make sure that I'm not making mistakes and that I understand conceptually what it is that we're doing here. And so yeah, this is going to give me some negative term. This is going to give me some negative term. And that should make sense for two different reasons. One, I look over here and I go, hey, both of these forces that are parallel with my displacement vector are going against it. So they are causing it to slow down. And that makes sense because the box is going to slow down. So that's one way that I know that it's negative. And when I look at these cosine of these values here, it does actually come out to be negative. Mathematically, that makes sense, not only from the angles there that we put in, but also notice that the right-hand side is equal to the negative of the initial kinetic energy. So then I go, well, if I have two negative things that I'm adding together on the left side, I surely am going to get some negative value over here. So that also makes sense. All right, now if I just clean this up and go throw in all of the mass there. Wait, I don't know the mass. But wait, hold on. Let's look at this closely here. M. I could divide both sides by M. And if I did that, this mass cancels out. Oh, isn't that beautiful? Now I go G. I know G. Delta X, that's what I'm trying to solve for. And V naught. I know that one. It started at 4 meters per second. So now I just go ahead and clean this up. I put in values I know and rearrange and solve for delta X. Here we put in the values that we already know, and then we cleaned all that up and solve for delta X, and you can go do that algebra off to the side underneath here, and we get delta X is 1.54 meters. That's it. Have a beautiful day.